Now, I think there are many benefits towards this, and I just list here a few. Of course, we can learn bespoke waveforms, new constellations, pilot schemes, which could especially embrace hardware limitations and imperfections. So rather than fighting this, optimally adapt to it. And the advantage of this would be that it could actually lead to faster development and deployment time, because you don't need to build custom implementations for every hardware setup, but actually learn an optimal implementation for each of these things. And simultaneously, with respect to standardization, if you think on a protocol level, it could actually happen that the standardization effort could be reduced. There's a lot of things that go through a lot of political debates, and they're not driven just by technical performance, but by competing commercial interests. Maybe this could be better learned by machines. If you just focus on the kind of, here's this another schematic that kind of shows the way I currently think about the potential of machine learning for communications, is that we actually are now able to optimize a kind of a communication link from end to end, but not with the goal of actually transmitting bit streams anymore, but actually serving an application with data in the most efficient way by taking into account, of course, the data itself, hardware constraints, the specific environment, and the needs of the applications. But this whole process can actually be, I think, the ultimate goal, which you be able to train these things as specifically as possible for certain environments, etc. And I think some people call this post-Shannon communications. I don't know if this is the way how I like to think about it, but I think it's to some extent a shift away from you have traditionally built communication systems. And yeah, and so with this is kind of the high-level motivation of what we're doing and how we think about the potential of machine learning. But now I would still like to focus on learning to transmit bits in the most efficient way. Okay, and this is what the first paper is about. So I put in the abstract, I put these two links to the archive paper. So the first paper is this one entitled End-to-End Learning for OFDM from Neural Receivers to Pilotless Communications. Okay, so I go immediately now into the system model so that we're on the same page and develop it from there. And by the way, interrupt me immediately if you have any questions. So don't write down slide numbers. I'm not sure if I have any. I don't. So I don't have slide numbers. So just interrupt me immediately. Okay. So we focus here on a SISO point-to-point link using OFDM, and we always look at a TTI, so a transmission time interval of 14 consecutive OFDM symbols. So this is, for example, a slot in 5G. And we look in the frequency domain representation. So it gives us actually a channel model where we have a matrix Y. So this is essentially number of subcarriers times number of OFDM symbols. And in our case, this is 72 subcarriers times 14 OFDM symbols. And now X is what you transmit, H is the channel, and W is noise. And to make things interesting, we assume a doubly selective channel, so where we have correlation across frequency and time. And if you vectorize the channel matrix H, it's actually a complex Gaussian random variable with covariance matrix R, which has the Kronecker structure. So where you have one component that is RF, which is actually describing the frequency correlation. And this is computed from the delay spread and the power delay profile. So here we use the 3GPP, TDL, A, B, and C models. And the time domain correlation, this is just a Jakes model, which depends on the carrier frequency and the speed at which a user is moving. And so we generate these channels just by filtering a Gaussian IID vector according to this matrix R. Okay. Now, in order for our essentially a baseline system to work, we typically transmit pilots on some of the subcarriers and OFDM symbols. We look at two different 5G patterns here. One is, we call this the 1P pattern and the 2P pattern. In the 1P pattern, you have only pilots on the third OFDM symbol on every second subcarrier. In the 2P pilots, you have an additional OFDM symbol. I think it's the 12th. We have pilots again. And so these are used to estimate the channel somehow, and all of the other resource elements, so these white rectangles, this is where the data is actually being transmitted. Now, I would like to present two baselines first, because that's what we're going to benchmark ourselves again. And I think it's very important to make these bad baselines good, because if you choose a bad baseline, then it's very easy to beat it. And we try to actually come up with the best possible baseline we could think of. Okay, so the first one is a non-iterative baseline, where we first estimate the channel across the entire resource grid using an LMMSE estimator. So there's not, I think it's very difficult to be better than that unless you take data into account. And so the way we do this, actually, we generate a data set where we generate many realizations of the channel. And you will see later that we actually have a channel model where we vary between TDLA, A, B, and C models with different delay spreads, different users. So it's actually a a mix of many channel models, and we essentially compute from this huge channel data set one covariance matrix for the entire vectorized channel. This is, this is quite large. So it's actually almost a matrix of the size 1000 times 1000. This is what we use to estimate the channel everywhere. Then we use a classical demapper, which computes the exact LLRs. So it's not the max log approximation. So it really, you assume it's a Gaussian channel and compute exact LLRs. We do some interleaving across subcarriers to get actually some diversity. And then we have a textbook BP decoder running 40 iterations. And actually, even the demapper takes into account the knowledge of the covariance matrix of the error of the channel. So this is taken into account. So when we compute the LLRs, this is another source of interference, which is actually taken into account when we compute the SINR for each resource element. Okay.
Can you clarify, is this a block fading model? Like after each slot, what do you assume about correlation?
Every TTI, we only look at one TTI at a time. Coding is done across this TTI, and everything is in there. And but from block to block, there's no memory or whatsoever. So okay. You get it's block fading. So it's not. But this is roughly to. We took this because this is roughly to the way I think many commercial systems work right now, where you would not be guaranteed that the same user was scheduled exactly on the same kind of PRB, so that you do some kind of maybe Kalman filtering, so to track the channel even better. So that's why we assume you get this one TTI, everything, that's all you get, no more information. And you're able to actually learn kind of the channel covariance matrices because you have access to a lot of data, but that's it. Okay, good. But you can do even better, as I said. So you can actually try to leverage data for semi-blind channel estimation. And that's what we call the iterative baseline. And this was kind of the best baseline that we could come up with. We think, okay, this is really the state of the art for this type of channel model. Maybe you guys know something better, but we couldn't. We thought, okay, this is possibly the best you could do. And what's going on is as follows. So we do the full-blown LMMSE channel estimation. Then we demap the symbols to compute LLRs. Then we decode them. So we run, I think, 10 iterations of BP decoding. Then we extract, so then we take the output LLRs from the decoder. Then we use essentially now these LLRs to compute soft symbols, which are used in the channel estimator to make a better update. And we extract what's called the extrinsic information. So the difference between the LLRs you feed into the decoder and what comes out. So essentially only the information that's provided by the code on top of the information that you had in the essentially in the observation. This is what you use to make an improved demapping decision with the updated channel estimate. This is quite, some people call this the APP kind of iterative estimation and detection and decoding. So this is how this works. And but in essence, you can think about it that this is a form of data-aided channel estimation. And typically this improves things if you run this for a couple of iterations. And this is expected to work well precisely when the channel is changing, not too rapidly, but rapidly, so that you have some form of channel aging in between your channel estimates. And this helps you to track the channel better across the OFDM grid. Okay, I didn't provide you any equation because I think this is kind of textbook material and this is stuff from the 2000s. So Stefan T. Brink and colleagues, they were looking at this like 20 years ago quite extensively. And then that's what we took. Okay, now coming to actually now our neural receiver. So because first of all, we wanted to look at what are the improvements we can get thanks to machine learning just by improving receiver, and then see what additional gains can we get by making the transmitter more flexible. Okay, and let's focus first on getting a good neural receiver. And maybe I go up. Okay, so maybe I'll go to this slide first. So 3 colleagues from us in Finland, so around Mikko Honkala, they've recently written a paper. It's on arXiv called DMRSs, and they look exactly at the same setting. And what they had this, I think, very good idea to actually, first of all, I look at a full grid, a full TTI of OFDM symbols, and then leverage a fully convolutional neural network architecture that outputs directly for every resource element on the grid the LLRs. And what's very important about this architecture is that you use dilated convolutions. So for those of you who do not know what this is, so typically in a convolutional layer, you have these filters. For example, a 3x3 filter. It's a small matrix that you swipe all across the input, and you compute a normal convolution. And this means that one element of your essentially output has a receptive field in the first stage of 9 elements. It can only see 9 elements. If you use a dilated convolution, you essentially make a bigger filter, which is mainly filled with zeros. So that's the way I can think about it. But so this means that now with this bigger filter, the receptive field of the output is dramatically increased. And if you now take a fully convolutional network where you increase the dilatation in each step a bit, you can quickly reach an output where every output element is connected to all of the input elements. This means the LLRs that you compute can actually see the full grid. And that's what you need if you would like to work with very sparse pilots, for example. You must actually be able to propagate information about the channel that you can learn at some part in the grid and use it elsewhere. And this is just a very efficient way of doing it without like this complexity of having dense layers everywhere. And further to reduce complexity, they actually use this separable convolutions, which just reduce the memory requirements. So essentially you have first filters that you apply to each input layer, and then you have just essentially a 1-by-1 convolution that mixes all of the output layers together. And for a very large number of layers, this is much less memory intensive than classical convolutions. Okay, and so this architecture works incredibly well. So they've shown that you can reduce, essentially you can go to 10% of the pilot the pilot patterns that you've seen in this slide. So essentially you can even remove most of them here. You just need a very, very small number of pilots and you get close to perfect CSI performance. Okay, so this is the architecture we use, but we used a bit smaller one. So it's just inspired by this. So here, so essentially you take your input matrix Y. First of all, you simply split the real and imaginary part and stack them together. So you have 2, and your input has 2 input channels. So it's a tensor size 72 × 14 × 2. And then you have many of these, I think 5 of these ResNet blocks, where you always have batch norm, ReLU, separate convolution, batch norm, ReLU, separate convolution, and so on. And you have these skip connections in between. And finally, the output is just a matrix of a tensor of the same size, but so it's have 72 times 14, and now I think we use 16 for QAM here. So this means you have 6 bits of information, and so at the output you would have 6 outputs for each resource elements. Okay. Any questions about this architecture so far? Or is this clear? Okay, good. Okay. But this model starts to be fairly big, huh? So that's not so that in terms of complexity, this is not lightweight. So that's if you look at complexity, it's you can reduce this. So we have never tried here to really reduce this, but it's it starts to be quite complex. So the computational load of these convolutional layers is quite high actually. Okay.
So for this DeepRx that you just explained by your colleagues, this was more of like a proof of concept, not something that they proposed actually implementing. It was
so the thing is, now that they know that this works so well, they are actively working on shrinking down the model complexity, quantizing it, making it work for MIMO. So you just did a paper where they tried the same thing for MIMO, and they actually get the same kind of performance. You need to do some tweaks, but this was also incredibly well, but the complexity is even higher. But I think it's what I find extremely nice about this, that this shows you kind of the, I would say, the upper limit of what you could possibly do. And for the time being, we struggle actually to come up with a classic baseline that would achieve the same performance. So even if you would say, there's no complexity constraints, do whatever you want, unless full-blown maximum likelihood detection where you would solve numerical integrals, we haven't been able to come up with something that achieves the same performance. And that's kind of, I find this intriguing. So it would be, okay, good. Now, the way we train it, this model is as follows. So, so essentially, so you generate a batch of these grids, so S examples of Y, for which you know the ground truths. Then, so this is indicated by L, so L range from 1 till S. Then you see that Q, so this QI, so this is essentially the output of the neural network at the case resource element for the ith bit. So you have one output for each bit on every resource element that's been transmitted. And think about this as this is a sigmoid function. So you have a sigmoid loss for each of them. So this can be interpreted as the posterior on the estimated bits you have given the full grid of the received symbols. So this is what Q is. So QKI is the estimated posterior of a specific bit given all of the input Y that you've received. And so this is essentially just the sum of the binary cross entropies of all of the bits that have been transmitted. And that's kind of a natural training loss for anyone working in machine learning. You say, okay, this is many binary classification problems, and that's a natural loss. But the nice thing about this loss is actually that it has a very, very good information theoretic motivation. So I'm convinced that this is precisely the loss we should use for communications. Now I'll explain you why. Because you can actually rewrite this thing in a different way. And I've done this here. I think I'm missing one term. Okay, so I think I've missed out one thing. So you can write this essentially as the entropy of your source, which would be m bits, and now minus the quantity that comes on the next slide. So minus r. And this r is actually the sum of the bitwise mutual informations. So this is a strict lower bound on the mutual information you would get if you would take the vector of all of the bits. So it's essentially the mutual information between symbols and Y. This is the bitwise mutual information that you sum everywhere. And you can see this is something which does not depend on the receiver. it only depends on the transmitter and the channel. So this is because this assumes that you had a perfect map receiver. So this is something that you can't do better than this. And now the second term is the price you pay because you're also learning the receiver. So you have essentially a mismatched detector. And so this is just essentially the KL divergence between the optimal posterior on the bits. So this is PBKI and QKI, which is actually what comes out of our neural network. So this is the loss due to the imperfect receiver. And you can imagine that the bigger you make your neural network and the better you train it, the more you can bring down this loss. And then what you're actually training on is you get something close to the bitwise mutual information. Okay. And here's, by the way, also now if you would give more freedom to the transmitter, then by shaping the constellations differently and the bit labeling, you could actually improve this first term. So this is where you can control things by doing things better at the transmitter side and getting this KL divergence small. This is what you do at the receiver side. And it actually turns out that this quantity R that I have here, so this you can prove that this is an achievable rate for a practically bit interleaved coded modulation system with a mismatched detector. And so and which you can actually achieve using bit-metric decoding. And that's what we do. So BICM with bit-metric decoding, that's what's done in almost all commercial products. That's like you use a LDPC code with a bit-metric decoder such as belief propagation. So we are directly maximizing, we're directly improving the performance and bit error rate that we get with a practical code. And that's why I think that's super important. It makes sense. And that's why we care about actually in most of the things we do in our research department, really try to impact products. So we really care about the specific metric here. So
just to clarify, so this is like kind of inside of an LDPC code. You're doing this optimization inside a code, or does this includes the code? This like basically
you have the code sitting outside of it. So the receiver provides these estimates. It's like the LLRs. Yes. And then the code sits on top.
That's what I mean. So yes, so this is like, in a sense, it's kind of like an inner code.
Yeah, exactly. It's but they have actually, in our case, there's not even a code because we just, for the moment, we use QAM and there are no coding gains. So it's just optimizing. We really care about getting the best LLRs we can. That's what we try to do. So, okay. But this directly impacts. If you see, whenever you see an increase in R, you immediately know that the bit error rate curve will get shifted by a fraction of a dB in SNR. So that's it. Okay, good. Now I wanted to, before showing results,
can I ask a question, Jakob? This is Krishna. So you mentioned that you had a model for the channel, which was like a JX model. Yeah. So when you train the neural network, do you train it based on data that's generated according to this model or with actual measurements?
No, we train here on, like, so what we, yes, I skip ahead to show you. So we actually, we do everything in simulations for this paper, but we generate this JX model over many different speed ranges, so ranging from 0 till 130 kilometers per hour. We vary the delay spread from 10 to 1000 nanoseconds, and we train on the TDL B and C power delay profiles, but actually evaluate on the TDL A power delay profile. So we really tend not to overfit onto a specific channel model. And there's another reason why we actually can't do this with measurements. And the problem is that we cannot get this data in the lab because we can't move at such speeds. We don't have interesting delay spread ranges. So we simply don't have the setup that would allow us to generate these type of channel realizations. So that's a big problem. So we have, of course, in our lab, we have software-defined radios that could do this, but the channel is just too boring. So actually, we cannot make it challenging enough in these settings. So it would be very very important, I think, to get real data for this, but this requires, I think, a massive effort.
So I have a quick, thank you very much. I have a quick follow-up to that. So when you said that the neural receiver was substantially better than your baselines.
Yeah,
so,
I will show the results later. Yeah.
Oh, okay. If you're going to talk about it, I'll wait.
Yeah, I will. I have many examples about this, and maybe let's discuss them. Okay. Good. So now I wanted to speak about essentially improving this first term here. What are the things we can do? And so there's one thing we can let our transmitter do that's called geometric shaping, meaning you want to improve simply the constellation and the bit labeling that's used compared to, I think we use here QAM 64 QAM constellation. And so this means we make one very small component trainable in the transmitter. It's essentially we have a matrix C tilde. In our case, I think that's size 64 by 2, because we have 64 constellation points and real and imaginary part. And then we essentially make sure that this is trainable. These are trainable weights. And then we make sure that we center it, so it has 0 mean and unit norm. So it just conditions any kind of, so it's compatible. You're not cheating with respect to the baseline modulations. And so it's also important, so we center it to avoid DC offsets. And we also prevent the system from learning superimposed pilots, because if we had a constellation with a non-zero mean, this would work as a superimposed pilot. And that's also something we don't want here, okay? And so this means there is really, okay, and by the way, so this constellation, this is used all across the resource grid. So we are not using any pilots anymore. This means all resource elements are used for data transmissions, no dedicated pilots anymore, okay? And so now we train this together with the neural network-based receiver that I've shown earlier, and then to see what is the performance you get, okay? Clear to everyone? Okay.
Yeah. So wait, how did the I missed this? Maybe I'm sorry
Yeah.
to explain this. How do the pilots get superimposed? You know?
No, nothing. There are no pilots, not at all. Nothing.
Okay.
No pilots, no dedicated pilots, no superimposed pilots.
Okay.
Just constellation. We use the same. We learn one constellation that is used all across the entire resource grid.
Yeah, I'm just confused. What's this bullet down below saying provides the learning of superimposed pilots? What do you mean?
Oh, sorry, it's a typo. Prevents.
Oh, okay. 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 All right, sorry. Okay.
No, actually, I understand the confusion. No, it's prevents. We do this specifically to prevent learning from superimposed pilots. Okay, we want to make sure that so the mean, at least the mean, cannot be used to say anything about the channel. Maybe the shape of the constellation can tell you something, but it's definitely not the mean. Okay. Okay. So that's one option we look at. And then we looked specifically in an alternative based on superimposed pilots, where we say, okay, essentially, could we learn, so we take a classical constellation, but could we now somehow learn to distribute some additional information all across the resource grid to make the performance better? And so the way we learn this is as follows. So essentially, so we take we generate classic we generate our QAM constellations, which are used all over the grid, and then we train a matrix A tilde. So these are weights which has exactly the same size as our resource grid. We apply a sigmoid activation to it, so that everything is between 0 and 1. And then what we are transmitting is essentially we scale the QAM symbols by 1 minus A. So this is always element-wise. And then we add essentially we have a pilot sequence generator, which is just random, I think random QPSK symbols, which are then multiplied by the remaining part of A, so that we transmit the same power. And essentially this means you're learning what power to dedicate on each of the resource elements for data and what for pilots. And you can train this and you can actually learn this. And we give this as additional information to the neural network-based receiver. And the reason is we didn't want to learn a specific superimposed pilot sequence, but a random one, again, to avoid that there are any DC offsets and so on. Since you could have a random number generator with a specific seed, and you know at every time this is what has been used. Okay. But actually, this is not the scheme I'm actually believing into, but we just provided this to see how much better or worse this could be against the scheme without any pilots at all. But it's also nice to see that you can learn this. And I think there have been many papers like also 10 to 20 years ago about optimum trade-off between training and pilots and so on. And you can actually learn this here for any given channel model, and not with the goal of maximizing mutual information, but actually maximizing the this achievable rate I'm speaking about. Okay, good. Now let's jump into simulations. So we have seen this earlier. So we really try to train across a very vast range of channel models and realizations so that we are not overfitting to anything. And so this means we train on all possible combinations and channel models. And then we evaluate this model. It's only a single model that has been trained. And then we evaluate this under different conditions. So we focus on 3 different speed ranges, like walking speed, driving in a city, and highway speed, and also 3 different delay spread ranges, and on a different delay, power delay profile, which we haven't used for training. Okay, good. Now I would like to focus first on just the neural network-based receiver with respect to our baseline. And I think, Krishna, this is, I guess, where you might have maybe now the time then to ask your question. So this is for this one pilot pattern where you have only one OFDM symbols with pilot, the third one. And so this means actually when you're moving fast, the channel will age very quickly. And towards the end of the TTI, the channel estimation gets really terrible and you take a huge performance hit. So you have in blue, perfect channel knowledge. Then in orange, this non-iterative baseline I explained. And in green, this iterative kind of data-aided scheme. And then in red, the neural network-based receiver. And you can see that at low speed, this iterative scheme works quite nicely. And you get actually gains over the non-iterative baselines, but at very high speed, also this iterative scheme dramatically fails. And I think that's something known. And I think it's simply a result of the fact that the channel estimates are so terrible that the soft symbols you compute to be actually used as additional data are more harmful than providing any benefits. So with this scheme, at least, you cannot, on these challenging, very fast changing channels, this doesn't help. And the neural network-based receiver, I think, achieves quite impressive performance improvements here. So I find this quite remarkable that this works so well. And as I said, I wouldn't know what to do better to actually make this work in this setting. Maybe Krishna, do you now you have a question?
Yeah, it's very interesting. Oh, I'm sorry, go ahead.
No, go ahead. Sorry.
Okay, so the thing that somewhat I don't understand is, so let's say you take the medium speed result and look at the SNR, let's say 17 dB SNR. So your iterative receiver has a bit error rate of 10 to the -2.
Yeah.
So you're getting 99 out of 100 bits correctly at that point. Yeah. But when you feed this back to the channel estimator, why does the channel estimator not perform nearly as well as knowing the channel exactly?
It's a good question. I don't know. I think it's not good enough.
But that doesn't say, okay, if you look at the low speed at 14 dB.
So okay, no, put it differently. So one way I think about it is, if you would look across the bit error rate, if you would look at the bit error rate distribution across the grid,
okay,
then most likely what happens is that at these you get these bit errors towards the end of the grid, and you're never able to correct these few. So there are parts that you always get right, and there's some bits you never get you never get corrected, even through your code. And you keep making these errors and you can never recover from this. So that's one way of thinking about, I think that's what's happening. But we have never looked into the statistics of bit error rate. But that's why I think that's what's happening, I think.
Okay. My other guess was it's probably bursty.
I'm not so sure because the channel, I mean, we ever look at 72 subcarriers over this time. So it looks that and we do interleaving, by the way. So we actually do some interleaving. So I actually think that it's not bursty. So but maybe Faisal, have you ever looked specifically into any of the statistics or anything like this?
No, but I think I agree with you, Jakob. I think I think that where we get far from the pilot, the channel is not recovered correctly, and this is where we get most of the bit error rates. But I think it's a good idea to have a look at this. To see
but I mean, the thing that's still, I mean, it's the same point. The thing that puzzles me is, if you look at the low speed at 14 dB, your bit error rate is 10 to the minus 4. Like, you're really not making any errors at all. It's like your bit exactly. I feel like unless there is a model mismatch, I feel like you ought to be able to get extremely good estimates of the channel. Question is there a model mismatch somehow? Like, are you taking into account the velocity when you actually do the correlation in the estimator?
So the problem is that we use a single covariance matrix estimated across the entire set.
That's a big problem, right?
So, yeah, but this is to be fair with the neural network based with the neural network that is not we don't feed the neural network with any estimate of the speed or the delay spread. So for fairness, we had also computed one correlation matrix over the entire possible range of speeds and delay spread. But yeah, maybe by computing a correlation matrix that is specific to each setup, we get better results.
But okay, I don't want to.
Okay, no, but hold on. But there's one thing. So okay, now I know we are actually one pilot pattern scheme here. So meaning you cannot exploit time correlation a lot. You get just one pilot for each subcarrier, and it doesn't actually help a lot. If you have two pilots, then it makes a huge difference. But if you have just one pilot, you cannot really exploit the time correlation nicely. So the interpolation.
No, but you know all the data bits. You don't need any pilots anymore. Your error rate is 10.
But then you also don't need any covariance matrix anymore, right? So if you know the
no, you need the covariance. Anyway, we can talk about it later. I think let's go on.
Okay, good. Okay. Now I have results for the 2P setting. And there you can see that with two pilots, actually there's not much you can actually gain. So it means because of the LMMSE channel estimation, you have extremely good channel estimates, and there's hardly any difference between the iterative and non-iterative scheme, and the neural network-based receiver, is essentially getting the same performance. So there's not much of a difference. So the key conclusion is essentially where this kind of neural network receiver shines is when you either have a channel that changes extremely quickly, or when you have just a very few pilots. But if you are having enough pilots or the channel is static, then a classical scheme just works fine. Okay. Now we looked at what happens when we give more degrees of freedom to the transmitter and do geometric shaping or learn superimposed pilots. And that's what you can see here. And there are now many curves, and I don't want to explain them all, but I think what you can see from this is that you get roughly the same performance as the baseline schemes. But the difference is you essentially get the same bit array performance, but you don't have any pilots at all. So that's the difference. And so it means the gains where I see it from actually geometric shaping or end-to-end learning is not an increase in bit array performance or anything like this, but it's actually, there's an advantage of getting totally rid of pilots. And the advantage of this is, of course, the throughput gain. So that's what I've shown here in these slides. Again, there are many curves, but just to give you a feeling, if you get rid of all of the pilots, depending if it's a 1P or the 2-pilot pattern, you gain between 3 to 7% in good put. So that we are putting here, and so that's a tangible gain. I'm not sure if this is sufficient to justify the kind of increased complexity, but I think there's also the advantage that if you look at 5G right now, I think there are specified more than 40 different pilot patterns. And there's control signaling for actually choosing which pilot pattern to use. There's a lot of overhead related to this. And I think with a single learned constellation, I think we have it somewhere, which looks like this, by the way. So this is this constellation, which is used all across the resource grid. You can actually use this all the time, independent of, what does the user speed, what's the delay spread. You can just use this and you get kind of the same performance as you would get with a very good pilot-based scheme. And there are no superimposed pilots, anything like this. Through the learning process, you get the bit labeling also for free. So that's because we train on this bit metric decoding rate. And for example, you can see, if you look at this, I don't know, can you actually see my mouse? No?
I can't.
Yes.
Okay,
Yeah.
maybe if you look at, I don't know, pick any point you want and look at the surrounding points, and you can see that this is actually a gray labeling. So it will only differ in 1 bit. So it learns kind of, and this is an optimal bit labeling together with the constellation shaping that learned.
There might be a laser pointer feature you can use as the presenter. Yeah.
Pointer option. Oh yeah, laser pointer. Yeah, so I know if you look, for example, at this bit here, you go to this neighboring bit, this just differs in the first bit position. The neighboring one, this differed in the 3rd bit position. You go to this upper one, this differs in the last bit position, and so on. So this seems to be a fairly optimal kind of labeling constellation. And the reason why, by the way, so now, why does this constellation work together with the receiver? And so first of all, this constellation has a single symmetry axis compared to QAM, which has 2. And this means that if you now, the receiver looks at the entire resource grid. So it sees many examples of points from this constellation. And because of the single symmetry axis, it's actually able to kind of know how it should back rotate, essentially. Essentially it can estimate the channel everywhere. So everything is useful because it can detect how it has been rotated to some extent. So this constellation only works together with a receiver that looks at the entire resource grid because they are jointly optimized for each other. So I think it would be very difficult if you use this constellation with a symbol-wise kind of detector. It just would catastrophically fail because you couldn't. Okay, good. So.
And Jakob, are you considering this kind of like in your mind? Is this a downlink or is this an uplink?
It can be both. It can be both. So
the pilots are quite different in the 2 directions, though, right? Like the way the pilots are. I mean, isn't there quite a bit more pilot overhead in the uplink?
So I think as the DMRS. So this would be, for example, this could be coded. So it could be pre-coded. So it's essentially you have a pre-coding. You send to every user gets a different stream, and within the stream for a specific user, you have the DMRSs. So this could use this at the UE side and the downlink. In the uplink, it would be identical. I mean, you have first of all the SRS, but then after pre-coding, you still have the DMRSs in the different streams, and you wouldn't need them anymore. You would still need, I think, SRS to actually estimate the channel matrix, because this you can't get rid of this. But within the kind of pre-coded streams, then you wouldn't need any DMRSs anymore. That's one possible way of how this could be used. Okay. Then I just wanted to show you what happens for this learned superimposed pilots. There's not much interesting happening, so that's why we just had it there for comparison. But it simply learns to allocate it allocates a tiny bit of the energy to pilots everywhere. And for some reason, it allocates more power to the beginning and the end of the TDI and around the borders. But we had a lot of discussions about this, and we believe that this is an artifact of the fully convolutional. We use actually a convolutional network to generate this. And so we believe that, that this is an artifact of our neural network architecture, and there's probably no specific reason to this. Okay, so that's not much. So the other interesting thing about this, so this constellation here is, of course, what would be the, is there any impact on PA, on the peak to average power ratio? And it turns out there isn't. So if you look at the PA-PR distribution for QAM, geometric shaping is essentially identical. I'm not a PA-PR person, so I guess someone who has worked a lot on this would immediately know that with OFDM, I think it doesn't matter much how you change the constellation on a per symbol level, and basically it doesn't impact it. I don't know. Is this right? Does anyone know this?
Yeah, I mean, with it doesn't have that much effect once you add all the subcarriers together. That dominates the actual constellation.
Right. Exactly. And yeah, so that's kind of the end of this first part. And I think there are two components. I think that this fully convolutional neural receiver architecture is a very good idea at the receiver side to be used, because it can learn, I think, very efficient data-aided channel estimation and detection methods. It turns out that you can do this also for multi-user MIMO, but right now complexity becomes really an issue. And the benefits of learned geometric shaping, so we haven't looked into anything else here in this paper, it's just learning the constellation, would be that it could eventually allow us to get rid of DMRSs. And that's interesting. But now there are, of course, many more extensions. So for example, where I think I had the slide at the beginning. So I think where things become much more interesting is if you start to take hardware constraints into account. So for example, if you would like to get rid of DPD and you want to learn a signal with a much reduced PAPR close to constant envelope, that's something you could do. You could learn new waveforms. You could yeah, I think that's you could optimize these things for ADCs and DECs with a few bits of resolution. I've seen some good work from your group on this topic, but I can think you can push this even further. So I think the big gains of end-to-end learning will actually materialize once we take into account hardware constraints, because for these classical models, I mean, I think we are doing fairly well. Okay.
Agreed.
Any questions on this topic, or shall we move on? I mean, we can also have a discussion now about end-to-end learning before we move to a totally different topic on protocol learning, if you wish. So it's up to you.
Hi, I have one question. So in your constellation, it seems like the I channel and Q channel are not symmetric, right?
One doesn't, if you rotate it correctly, yes, I and Q, you could make it that they are one half is essentially independent of the other.
So
I mean, I'm not actually sure if this is even true. I haven't looked at if this labeling is such that you can really separate things as an I and Q, but maybe you're right. I haven't looked into it.
oh, and also the noise, the effect of noise will be high where in the center part of the constellation, right?
Effect of noise. Yeah, it means definitely that the bits which are close to the center, they carry less information. They are more prone to noise. So that everything in geometric shaping is about this essentially. You have a few kind of points which high energy, which carry kind of more information or protect information better than those that are closer to the center. So for example, if you would train this at, so we have trained here specifically a single constellation across all of the SNRs. Uses, we wanted to use it across all channels, all SNRs, just one constellation to make something practical. But if you would optimize this for a specific SNR, you would, for example, see that as low SNRs, the constellation would collapse to a few points because the system has learned that I cannot convey more than 2 bits of information anyway, so there's no need of having more points. So this constellation takes all of this kind of into account.
Oh, okay.
So if you would plot this as a function of the SNR, you would see that you start off with something which looks like, I don't know, a weirdly shaped QPSK, and then each point spreads out into more points and so on, because the system learns that there's actually more information that I can convey.
Oh, okay.
And then you would need to adapt the code rate accordingly. So essentially, if you make this SNR dependent, you have your constellation that changes, and what you need to adapt then is the code rate. So
I see. I see. Thank you.
So one question that is, do you assume that the channel, the encoder is aware of the, for example, the SNR and the channel state?
No.
Then how would the encoder know which learned constellation to use?
Oh, it doesn't. So that's why I said we learned here a single one, because we learned here just one where we have 64 points that you would like to use across the entire SNR region. Just find one which works well. And now if you wanted to make this more practical, you would learn maybe 3 or 4 constellations, like QPSK 16 QAM, 64 QAM, and 256 QAM. And you could just use these instead. And then together with a couple of different codes, you could actually get these nice, you could do link adaptation as it's done classically. But you could also, so the thing is, you could also have essentially a neural network that would permanently adapt. So you actually feed the SNR as an input into it. And for every SNR, it generates a different constellation. So we have done this. This provides you even better gains. But the problem is that you would need to have quite precise SNR information at the transmitter, which you don't typically have. And so, but you could do this, yeah, and you would even see the better performance improvements.
Okay, I'm just trying to understand, like, so my understanding of using pilot signal is to estimate the channel and then adapt what to do accordingly. And then you're saying like you don't need to do that.
No. We don't. So essentially, we don't do any link adaptation here. So what's fixed is, the only thing we fixed is you have a constellation with 64 points.
Right.
And then we maximize for maximum bitmetric decoding rate. And then what code you choose to use, this would be up to the link adaptation. So it's just an example. Yes, there's no link adaptation going on.
Okay. Thanks.
Good. Okay. Then
any other questions on part 1?
Good.
Okay, great.
But there's another nice beginning. So you actually don't need a code to train this. That's there are some. I think what's also interesting is you could now on top of this learn a optimized code. So for example, you can use you can actually, once you have trained your transmitter and receiver, you can then on top of this learn, for example, or optimize using classical techniques, a very good parity check matrix for an LDPC code. And that's, we typically see in another 0.5 dB of gains for this. So now this is maybe not practical for cellular, but maybe one could imagine that if you think about the fixed, for example, backhaul links, you would really say, I learned one bespoke kind of constellation scheme together with the optimized code for this one link, and you can do this all in an automated fashion. So if someone, and you don't need to be standard compliant, so maybe it's a good use case, but in our company, people are not willing to do this yet. So let's see, but you could do this. So I think that's also an interesting area, and actually to actually combine this with coding, and I mean, I don't know your name. I'm not sure if I can pronounce it correctly. Heiji, or
yeah.
I mean, you are working exactly on this topic, so that's one of the next frontiers to actually combine this with learning in a single process everything. I think that's quite interesting.
Right.
But from our
Yeah.
Go ahead, sorry.
But there are like companies who are actually trying to build your network-based codes like that doesn't comply with standard, so it cannot be used for cellular, true for sure, but like for other other stuff like Wi-Fi.
Yeah.
Yeah.
No, that's true. That's true.
Yeah.
Okay. But maybe to give you a hint of where I at least think or at least where I know that I will spend most of my time next year is it's going to be about waveform learning and trying to especially looking maybe to terahertz spectrum and do this together with some massively constrained hardware. So that's I think quite interesting. And I mean, another interesting area is actually to do this, to learn this together with for a specific application. For example, think about, I don't know, surveillance systems, these kind of things where you would take the source coding aspect into account and also what you want to do actually with the data. So I think that's also interesting. But I haven't come up with very convincing use cases yet, and I always need a good use case before I start to work on something. So but I think that's okay. Then let's go to part 2. Now we essentially, it's actually natural to think about, okay, if you can learn the physical layer, can we learn the MEC layer? And that's now much more difficult, I think, and much more visionary. And so together with Alvaro, so we've started to look into this topic. And we just put a paper on archive called Towards Joint Learning of Optimal Signaling and Wireless Access. And it's actually, so the title is a little bit misleading because we are not at all doing this. That's why it's called Towards. That's what we want to do, but we are not able to do it. And we do a smaller step actually towards this goal because the problem is very difficult. Okay. So you all know what the protocol is, but I think it's for this problem, it's very important to kind of correctly set the stage. So a protocol is a MAC protocol. Actually, the only purpose of this is a user terminal and an access point, they negotiate how to transmit data. Okay, so the user wants to send some data, and there's a lot of control signaling involved just to make sure that the user gets the data across. So you're going through classic schemes, you have scheduling requests, scheduling grants, buffer status report, etc. But the only thing that matters is that at some point the user is transmitting data and maybe gets an acknowledgement. And this is similar to language. So essentially, we negotiate something as a goal. And another what makes this problem difficult, the point is not what I wanted at all, is that there are many users talking to a base station at the same time. And so the base station is negotiating in parallel with many users. And now, so the question is, can we actually learn such a protocol? And there are quite a few challenging things about this. And the first is, how could you actually even come up with a procedure that allows you to learn a MAC protocol? So if you replace a MAC by learnable components and to train it, it turns out that at the beginning, they will just exchange gibberish. There's no notion of predefined messages. They don't know how to interpret this. It's actually very difficult to make this converge anyway. Secondly, how do you actually quantify if a protocol has emerged? So how do you say, now I have learned a protocol? How do you measure this? And the third challenge is that this requires quite a lot of compute power. So you suffer from very slow convergence. You need many GPUs and CPUs to make it work. And this all makes this extremely difficult. And you will see later on why it's so difficult. Now, but why is this problem important? I think there are a few good reasons. First of all, cost. If you think about how protocols are standardized, I mean, I think there are billions of dollars put into this. People from companies all across are negotiating, going to meetings for a very long time. They all have competing interests and try to push their things into standards. And I think it's quite questionable that at the end of the day, with this cost, you reach the best outcome. And it's not about just the cost related to standardizing something, but also to implementing something. Implementing these protocols takes a lot of time. It's error prone. And one could possibly even think about just replacing the implementation of existing protocols through machine learning. Now then there's an aspect of performance. So you have essentially this idea, right now we think about what protocol machines should use to talk, but it actually lets machines figure out what protocol they should use might be a good alternative to this. And then there's mainly the scientific aspects to actually, we always struggle to understand why things go wrong. So why did the handover fail? Why does this happen, etc. But actually, sometimes I think that's maybe not really necessary. And it's also quite interesting from a scientific point of view, just to study these emergent communication phenomena and emergence of protocols to see what happens. So I think there's a bit of work in the machine learning literature, but I think not in the context of really protocol learning for communication systems. Okay, now what do I actually mean by a MAC protocol? Because when we started this work, I got very easily confused, and I think now it's clear in my head, but I hope I can get this across. So the way I think about this is that a protocol consists of a signaling and a channel access policy. Now the signaling consists of two parts: a vocabulary, which is simply the set of messages that you can send. Okay, like buffer status reports, scheduling requests, etc. So this is, you have this vocabulary that, like a language, this is what you can use to communicate. And then you have a policy, a signaling policy, which gives actually meaning to the vocabulary. It tells you what is the order in which you should, for example, exchange messages to achieve a certain goal, to convey certain information. And then you have the channel access policy, which essentially relies on the signaling to get the information it needs to decide when to actually transmit a packet or essentially use the physical layer. So for the channel access policy, the physical layer is like an API. It just tells send a message, okay? And so this is actually vendor specific. So even for a standardized protocol, the way you implement the channel access policy, this is not standardized, okay?
So is it fair to say that like this channel access policy, like in the uplink, could be like sort of your random access policy, like, you know, if I'm, you know, not being told what to do, this is how I would decide whether to contend, whether to send, how to sense, and so on, and under what conditions I would send. And in the downlink, it's how I allocate resources to users, where then the signaling is how I communicate that allocation. Is that like basically what you're saying?
I was thinking that, yeah, I think it goes towards this. Maybe let's make it maybe even simpler. So imagine we have a system where you can say I can send a scheduling request, and I get maybe from the base station I get a scheduling grant. That's what the signaling provides me to do. You know, I send this request. I'm lucky. Hey, you get a grant. But if I now actually take the opportunity to transmit or not, that's up to me. So if the vendor decides I have a shitty system where I only transmit, you know, once in a while when I get the scheduling grant, you can do it. It's up to you. So it's up to you actually. Essentially, the signaling allows you to say now you can actually you get resources to transmit, but if you do it or not, it's totally up to you. Or if you have the random back off or something, that's totally up to you.
But are you thinking of like here, I mean, I guess it's kind of different. Are you thinking about a centralized control system like a cellular system, or is this more a contention-based system like a Wi-Fi or unlicensed spectrum?
So
I guess it'd be quite different.
Yeah, so I think ideally the goal would be to merge something in between, where you can't really say is this now contention-based or essentially scheduled. And I think the optimum solution, I think, depends highly on the traffic and also on the interference levels and so on. And so for us, kind of the motivation also of this work is to go beyond these kind of fixed distinction between different ways to organize traffic and have something more fluid in between. And now with respect to where this might pan out, what I think is quite interesting is this idea of sub-networks in 6G. So essentially very specific networks, for example, to replace communications within a robot. So for example, where you have a sensor, a controller, and an actuator, and you replace cables by wireless connections. You might have many from them in the production hall. You have essentially a very small network with rather deterministic type of traffic. And you would like to learn the bespoke protocol for this type of network. So right now, I don't think, I don't see big potential for cellular just because of the complexity. So we come to this later. But I don't think within a reasonable amount of time, these kind of ideas will be mature enough to actually practically work. So that's yeah, that's the way I think about it. Okay.
So kind of ignore the base station UE sort of figure.
Yeah, I mean that's how we phrase this setup here, but it could be just a you have an access point and to transmit this. And just to be clear again for the what we mean by to make it even like another way of looking at the signaling. So essentially, there's this essentially the user only cares about sending data. So what gets traffic through the user plane. So that's what you see in the top right corner. You have user data. And you would like to send this to the base station in the uplink. And now everything you do, the signaling only is control traffic. And the goal of this control plane is to actually make the user plane work efficiently. And so in this paper I'm discussing about, we only focus on the uplink. So there's no downlink messages, so nothing from the access point to the user. But we have of course control plane signaling in both directions. How am I doing time-wise, by the way? I think horrible parts. Okay.
We're in a virtual world, you know. So I mean, I think you're the one that's like, I guess it's, you know, happy hour time over in Paris right now, or pick up the kids' time. So you tell us. I mean,
no. I still have some. I still have some time. I hear my son is there. It's already crying somewhere. But okay. So here just some examples. I don't want to go into it of different channel access schemes and the resulting MAC protocols. Now. Since this is just the beginning of this work, we have actually far more questions than answers. And there are two components actually to it. So the first is actually how well can we actually learn an existing protocol, meaning that assume that the access point is an expert. So this is an existing protocol. How well is actually possible for a user terminal to be able to communicate with the base station, with the expert. So that's what we mean by protocol learning. And then the goal, which much further out, is that of protocol emergence. So assuming that neither the access point nor the user equipment know anything advanced, is it possible that they jointly learn to communicate and emerge some form of protocol? Now, with respect to this first part is, so first of all, can we learn an existing protocol? And the second, and the reason why we're interested in this is, could protocol learning techniques actually replace protocol implementation efforts? So rather than having engineers doing this, could we just learn it? Because once you've learned it, you immediately have an implementation, and this might be much easier to do than a test, trial, and error. And with respect to protocol emergence, I mean, we simply don't know if multiple agents can actually emerge a protocol of their own. We do not know how to tell when a protocol is actually optimum. We don't know how to actually measure this. And then the latest question would be, can actually these techniques, could we bring this up to a level where they could actually provide meaningful protocol and maybe replace standardization efforts? Okay, good. And we haven't achieved anything with respect to protocol emergence yet. So I will therefore only focus on protocol learning. And so within this idea of protocol learning, we have a couple of questions we look at. What kind of learning techniques should we resort to? What's the computational cost? How does it train to do this? Is it even possible? And do we actually learn something that achieves a good performance? And once you've learned a protocol, how well does this generalize to different settings? So if you've learned, for example, a protocol where 2 users have been communicating, would it also work now if suddenly there are 6 users? Okay, good. Now we make things, actually, we've built the smallest toy model almost possible to look at this. So we have essentially 1 base station and 2 UEs. The base station is an expert, so that's not trainable. and the users are actually learning something. And so now what we have is we distinguish between channel access actions. So this is actually related to whenever a user is transmitting something, and there are just 3 actions. Either you do nothing, either you transmit the data packet that's first in your buffer, or you delete the data packet from your buffer. That's all the users can do. And then there are uplink kind of actions, signaling actions, and downlink signaling actions. So in the uplink, a user can either do nothing or send a scheduling request. And the base station in the downlink either sends nothing, or it responds to a scheduling request with a scheduling grant, or it sends an acknowledgement once it has received a data packet, like an SDU. Okay. This is so essentially we have fixed our vocabulary. So we know these are the messages, and the base station has a fixed signaling. So for the base station, we have predefined rules which tell you if you get a scheduling request, you respond with a scheduling grant to one of the users. If you get a data packet, you respond with an acknowledgement. That's how this is fixed and coded. But the users, they do not know anything about this. They just have these actions available. I can do some uplink signaling. I can take channel actions, but you have no idea whatsoever what this means, in which order they should execute these actions. So they need to learn this. And so now I will explain these notations later on. Just for comparison, and that's why the problem is so complicated. This is what's going on. This is the what's, for example, the specification of uplink messages in 5G on this shared channel. There are, I think, 64 different message types, and each of them can have varying payloads. So we are many orders of magnitude less complex compared to like a commercial protocol. So that's kind of the complexity to which one would need to go to make it work. Okay, good. Now the way we look at this problem is actually as a decentralized, partially observable Markov decision process. It's decentralized because we have these 2 UEs, and it's partially observable because UE only sees the downlink messages that has been sent from it to itself. So it cannot see the control message the base station sends to the other user. So so that's why they don't have full observations. Now, they essentially, the received observations are OO. This is essentially the buffer state. So it just tells them how many messages do I have in my buffer. So it can be 1, 2, 3, 4. And it gets the received downlink message, which can be essentially just a scheduling grant or an acknowledgement or nothing. And then it takes an action. So either it does nothing, it transmits a packet, or it deletes a packet from the buffer. And it can also send an uplink signaling message. So it takes essentially this channel access action and the control action at the same time. And it gets a reward. And then we move from state to state. And in every time step, you get a negative reward of -1. And the goal here is to maximize the accumulated reward. And we define an episode in a way that once all of the UEs have cleared their buffer, the episode is empty. So the goal of the learning is our protocol should ensure that all users successfully transmit their messages. So in the smallest amount of time. So that's what this reward tries to achieve. Now, since this action space and state space is quite small, we use multi-agent tabular queue learning. So there's no deep reinforcement learning. We can use classical techniques here. And so essentially, so we have within a UE, we have essentially 2 queue tables that tell you essentially the expected reward you get for a given action. And we have essentially 1 queue table for the signaling actions and 1 queue table for the channel access action. So if you transmit data or not. And the input we get, so is this buffer state, O of t at every time instance. We get the downlink control message, M of t at every time instance. And to actually make it work, we have a we have a memory in there that's H, which just accumulates the tuples of observations and downlink messages. So actually to give to actually have some time dynamics into it, so this memory is really helpful. And but just so that you get a feeling of how large these action space actually becomes, these tables actually become. So we have, I think, a memory of length 4, and in each of these tuples, you get all possible buffer states, all possible downlink messages, all possible actions that you could have taken, and in the all possible channel access actions and all possible signaling actions. And so for each possible kind of realization of this memory vector H, you get a different, you need a different essentially row in your Q table. And there are, I think, 8 million already possibilities in this. So these tables, even for this very simple model, become very, very large. It turns out that during training, you might only need 64,000. So there are many states that are never visited. But this is the reason why multi-agent, this is tabular learning, quickly reaches its limits, even for such a small scenario. Okay, good. Now we have the issue that we have 2 agents. And if they were totally independent from each other, we would run into issues with convergence. And so for this reasons, we actually only learn a single policy, which is used by both agents. But we actually gather the inputs, the observations, the experience both agents makes together to update as our single kind of Q table for both of them. So essentially, we gather transitions from all UEs, but we only have a single table or 2 tables, one for the signal actions, one for the channel access actions, which are used by both of the UEs. So meaning both UEs apply exactly the same policy. Yeah, so that's the way we train these things. Any questions so far? Maybe I'm moving too fast. Okay, good. Okay. Now let's look at first at how well we can learn so this existing protocol. And we started with something very simple. At the beginning of an episode, every user gets 1 packet. It's fixed from the start, and we see you know how quickly they can actually learn to get this 1 packet sent across the channel. And so if it's just 1 user, it's very easy to come up to the theoretical optimum that's in this purple line. When we learn it with a single UE, we achieve the optimum performance. But now if we increase the number of UEs, then you can see that we kind of start to outperform our expert kind of protocol implementation, which just respect this this exchange of I ask for a scheduling grant, I have a scheduling request, I get a scheduling grant, and I transmit a message, and then I get an acknowledgement, then I delete it. They actually announced that you can do a tiny bit better, and so we can outperform this here. So that's kind of good. And the reason why we can actually outperform is because we have the data channel has a block error rate of 50%. So meaning when you finally decide to transmit a message, there's a 50% chance that it just gets lost. And the UEs can actually exploit this fact and adapt their behavior. So the channel access policy, this is actually optimized for this one specific scenario. This just shows you how training proceeds, and then you can see in this very simple scenario, it takes roughly 250,000 episodes to train this, which is already quite long, given that it's so simple. But that's short. Now we made this a little bit more complex. So we said there's random traffic arrival. So at the beginning of an episode, there is no, you don't have any data in your buffer, and then with a certain probability, you get a data packet in your buffer, and every user has at maximum 2 packets to transmit. And when both of them is achieved to do this, then then the episode is over. There's a block error rate of 10%. And now you can see that here the training, we needed 8 million training episodes, which we've repeated several times. And this starts to take already a very, very long time on a standard CPU. And you still get good performance, but yeah, this shows also some quite severe limitations towards this approach. Now I just wanted to show you one example here where we try to actually understand what's going on. So and there's just one interesting observations we made is the following, and that's also where some gains come from. So when the channel the channel for data transmission is very reliable, then the users learn to ignore acknowledgements, because they essentially know that whenever I get a scheduling grant and I transmit, I'm certain that I had the spectrum for me and I didn't make any error on the data transmission, and so I don't need to act at all. For example, we see that this can be ignored, and so actually, so a user directly deletes a packet after if it transmits something after having received a scheduling grant, and that's where some gains can come from. So they learn to exploit this this gap. Okay, and otherwise, I mean, we spend a lot of time looking into what's actually going on, and there are many interesting phenomena, but it's very difficult to explain them. It just yeah, it just seems that you can use this existing signaling in many different ways to accomplish the same goal, but you don't need to use it in a way actually I think we humans wanted it to be used. So that is the most interesting conclusion I think you can get from this work. Then there's this question of how can we actually measure if we have learned a protocol. And I think this is very interesting. And so there is a way to actually measure what it's called instantaneous coordination, or the value of signaling. And this is simply the mutual information between the downlink message, so MT, you receive at time instance T, and the action you take in the next time step. And so if this mutual information is kind of high, then it means that the control message you receive actually impacts your action. And if it was totally contention-based, then the mutual information would be 0, because you say, I don't need any downlink signaling at all. And so, and what we show here is actually a plot where, so we have done many, during training, we have run many different kind of trainings. Oh, my son is coming. Salut, Simon. My wife as well. So, hello, everybody. Yeah, you want to? Yeah, okay. Simon. And so what you can see here is, so we have run different runs leading to different performances. And on the y-axis, you see the instantaneous coordination. And it turns out that good performance correlates with instantaneous coordination, meaning that there is a positive impact of signaling, because so the signaling impacts actually the performance. So and that's, I find this quite nice to actually see this. So you can this is a way to specify, yeah, the gain, the benefit of coordination. And I think this is quite nice. And for example, you can see that at very low block error rates, there's a lot of benefit in coordination. But when the channel is actually, and you go towards purple, where the block error rate is fairly high, then coordination becomes less important. And the reason is simply, if you get a scheduling grant, you transmit it, but there's a very high chance that your packet is lost anyway, then the gain of the coordination is totally vanished. Then we have some results on generalization, where we trained this on, for example, look at the right-hand plot. We trained this, for example, for 2 UEs, and then we tried how to make it work for more UEs. and you can see that it generalizes quite poorly. But what works is if you train it actually on a large number of users, it generalizes fairly well for a small number of users. But actually, even training this whole system for 4 users is quite challenging. So I think I had a discussion with Alvaro and said, "Why didn't you do anything for 4 UEs?" And he told me I couldn't make it work. So yeah, that's kind of. But there are tricks to do this, but it just doesn't work. Doesn't work like this. But it's fairly robust with respect to the block error rate. For example, you train on one specific block error rate on your data links, and this generalizes kind of nicely to different block error rates. So maybe I want to conclude here. So I think we have seen that kind of this MARL setup. So MARL is multi-agent reinforcement learning with centralized training and decentralized execution seems to be one way to look into protocol learning. The computational cost is extremely high. You've seen in these toy examples that you get theoretical performance. And sometimes for when we don't know the best theoretical protocol, we outperform baselines that we've implemented ourselves. And so there were some unexpected results. For example, that the UEs learn to comply to signaling, but that some signaling only arises in certain challenging scenarios. So in some scenarios where it's just simple, our system has learned that the signaling is not needed, and for example, ignored these ACK messages. Now moving forward, so we actually now looking into making this more interesting, come up with more challenging scenarios, to actually be able to see how much we can improve upon expert max. We're going to look into how to make this scalable by moving away from tabular learning towards deep reinforcement learning. We have this problem of generalization, and I have no idea what zero-shot coordination is, to be honest. So I think Alvaro, you would need to explain it. And then, I mean, one could even go one step further and think about why not learn protocols jointly together with the kind of the air interface, the physical layer. Because often I think we've seen that a MAC protocol is very specifically optimized for a given physical layer. And maybe by having both jointly optimized, there could be further gains to be had. But maybe Alvaro, can you comment on this zero-shot coordination? I don't know what this is.
Yes, sorry. Usually when you train
the
these
other
systems,
things I wrongly explained, so maybe correct if something was wrong.
No, it was good. It was good. Thanks. When you train the systems, it turns out that the agents that you train are highly biased to work well only with their training buddies. So with other agents that have been trained in the same way and converge to similar policies. And so the moment you actually confront these UEs with other different UEs, perhaps expert UEs, they don't work that well. So this idea of zero-shot coordination is that you would train a system such that when confronted with somebody, some other system that has not seen before during training, it works well from the outset. And there are some techniques to do that. But we haven't looked into this. This is just open for future work.
Yeah, and I think yeah, that's all I had. Yeah. Any comments, questions?